For atomic theory and bonding unit, lesson 8. So you will see this type of layout in your notes packet where I've laid out all of the main types of bonding, whether they're intra or inter. The big difference between that is that intra is within compounds, so one atom to another, versus inter is between molecules, so one water to another, for example. So looking at this, the intra bonds, there's three main types. There's ionic and covalent, which you've heard about, but there's also polar covalent. So ionic is going to be a transfer of electrons to form ions. It's between metals and nonmetals. You form a giant lattice of ions. You have to have an electronegativity difference between the two atoms of greater than 1.7. You have high melting points and boiling points, conducts electricity, and they dissolve in water. Okay. On the other end of that spectrum is covalent, where they share electrons, nonmetal and nonmetal. They form discrete molecules, so meaning just two of them together. It uses Lewis and Vesper. Low melting points and boiling points, does not conduct electricity, does not dissolve in water. So one type of covalent bonding you can have is coordinate bonding if the central atom has less than the number that it wants to have, which is 8. So for example, this BF3 here, this boron only has 6 in the middle. It can pair up with something that has a lone pair in the middle, so they can kind of share that extra set. And then London dispersion forces exist for everything that's covalently bound. So all covalent have them to some extent. It's due to just the electrons moving around between that shared bond. Okay, and then the larger the molecule, the more of these they have. So that's the intermolecular bonds between covalent molecules. So the thing that you probably haven't heard about is there's an in-between between ionic and covalent bonds. They're called polar covalent bonds. It has an electronegativity difference between 0.4 and 1.7. Dipoles must exist. We'll be talking about that in a minute. It cannot be canceled out by symmetry. To determine, you basically take these steps. So you draw a Lewis structure. You ask yourselves, are there any polar covalent bonds? Are there any lone pairs? And then if you have either of the things listed in number 2 here, you confirm with Vesper that they don't cancel out. Okay. So a dipole means that there's this area of partial negative and partial positive. In this case, positive, partial negative. If you look here, this one is a non-polar molecule because you see the chlorines are evenly spaced out versus there's only 3 chlorines on the bottom and 1 hydrogen at the top, so this one becomes polar. We're going to talk more about that in a minute though. But polar covalent bonds have dipole-dipole bonds. That's because of the partial positive and partial negative, so they're attracted to each other for that reason. And then most famous polar covalent bonds have hydrogen bonding, which you hear a lot about, especially with water. You need to have hydrogen bonded to either nitrogen, oxygen, or fluorine for this to happen. Okay, and then you've heard a lot about what happens because of hydrogen bonding in bio class. So we're going to look at some example problems to kind of work through the information that's in this infographic here. So looking at this, so we need to classify the bonds in these following elements: pure covalent, polar covalent, or ionic. Okay, so pure covalent just means regular covalent, as you've heard of before. Okay, in order to figure this out, first thing we need to do is just look at the elements we have involved. So H and Cl. We look here, the electronegativity values are what really matter. So hydrogen has an electronegativity of 2.20, chlorine 3.16. So if you subtract the two of those, you need to figure out, okay, where does my value lie? So if we look here, if it's greater than 1.7, it's ionic. Between 0.4 and 1.7 is polar covalent. And then less than 0.4 is covalent. Okay, if you want to add that over here, you can. So, okay. So looking at this one here, we subtract 3.16 and 2.20. That's about 1.96. I'm sorry, 0.96. Okay, so that's clearly going to be in the range of polar covalent here. The next one, hydrogen and carbon. Hydrogen's 2.2, carbon's 2.55. That's 0.35. Okay, which is less than 0.4, which makes it just a regular covalent. You can write pure to emphasize regular. HF, so 2.2, 4.0, that's a difference of 1.8. Okay, that's a very high value. That's, if you look back at this graphic, higher than 1.7, so that makes it actually ionic. Regarding the electronegativity differences here. All right, and then you can keep doing that for these other ones. But what I really want to start working on together are these ones down here. So if we decide if things are polar or non-polar molecules, we need to go through the 3 steps listed here. So you draw the Lewis structure, you decide if it's polar covalent or if there's any lone pairs, and then if we do, we need to draw out with Vesper. So looking at this first example here, SH2. So the first thing we need to do is we need to draw out the Lewis structure. So we count up, S has 6 valence electrons, each hydrogen has 1. There's 2 of them, so that's a total of 8 electrons. We have one S that goes in the middle, two H's on the other side. Each H only wants one bond. That's why we write one line next to each. Hydrogen can only have 2 electrons next to it. Okay, so it already has that. That means we have 2, 4. We need 4 more electrons to get to 8. So we put 2 sets of dots on the S. Okay, so we need to ask ourselves, okay, do we have any polar covalent bonds or do we have any lone pairs in the middle? Okay, so we very clearly have lone pairs in the middle. We could subtract the difference here. So S is 2.58 minus 2.20. Okay, so that's a difference of 0.38. If you look back at the table, not technically 0.4, but we do have the lone pairs either way. So we have to draw the VSEPR structure. Okay, so if you looked at your VSEPR table from your notes the other day, we have a 2-2 structure, 2 bonds, 2 lone pairs, which is going to be a bent orientation. Okay, so you're going to have something that looks like this. You've got a pair that's kind of going back in the computer and a pair that's coming out at you. Okay, so next thing you need to do is ask yourselves, okay, is there an area, clear area, like whether it's above or below or left or right of the central atom where all of the negative charge lies from the electrons, okay? So if you look at this, hopefully you can see very clearly above the S here is where all of these electrons are. So because there's that clear region where all of the electrons are, it's like there's a partial negative up here because of all the electrons. Remember, it doesn't actually have a negative and positive area or else it would be ionic, not ionic. So partial negative and partial positive, meaning there's this sort of area where all the negative is, sort of area where all the positive is. Because you can easily divide that up, this is a polar molecule. You can identify these areas where there's partial negative and partial positive. Okay? All right. So let's try the next one here. Try SF6. If you remember, we drew this one the other day, so I'm just going to recopy it real quick. Okay, so that is our total structure here, our Lewis structure. We ask ourselves, okay, do we have any lone pairs on the thing in the middle? Yes. No, we don't. Do we have any polar covalent bonds? So S and F, we subtract, that's about 1.62. I'm sorry, 1.42, which means yes, we have polar covalent bonds. So that means we need to draw the VSEPR structure. So we've got a 6-0 configuration, 6 bonds, 0 lone pairs, which means that our VSEPR looks like this. Okay, now we need to ask ourselves, is there an area where we have all of the electrons that have that negative charge, or is there an area where all of the really electronegative atoms are? If you can visualize this in 3D, the F's are evenly spaced all around the S. So since there's not a clear area where you can say all the F's are over here, all the F's are over here, because they're evenly spaced around the S in the middle there, we can't decide a clear area, which means this is nonpolar. So even though F itself is very electronegative, because they're evenly spaced all around the S, it cancels each other out essentially. So we have a nonpolar molecule. All right, so you can try out the rest of the examples you have for these, but keep that in mind. You need to clearly be able to find an area that has all of the negative in the electrons or the electronegative atoms. Okay, it cannot be canceled out by symmetry like it was with the SF6 example.